So these are vector fields on M, and I have some function that is just smooth function on M, like the temperature field, the temperature function on the earth, the pressure function or humidity or whatever. Okay? And these are vector fields. At every point gives you velocity vectors. Well, these are vector fields. This is function. I can always compute Ly of f, right? What is the result of this guy, please? What's the result, Ly of f? What's the result?
Function.
A function. Again, it's another smooth function on M. Nothing prevent me from doing this, right? Okay? Let's compute it, please. Lx acting on something, that's fine. I'm not scared. It's the summation over j from 1 to n. This is vector field x, so it's xj times partial little xj of whatever you have, right? What do I have inside? Well, I have another definition of the Lie derivative, or the directional derivative, which is, again, how to compute it. It's summation. I'll change just the name of the sum. k1 to n yj partial f, sorry, yk partial f partial xk. Okay? Any question about that? Any question?
Is it xk or yk?
Inside here?
Well, yeah,
Is
on
y.
the right, in red. Yeah.
Oh, it's with respect to the coordinates. It's the same coordinates of m, right? And the coordinates, you call them x. If you want to call them q, like our q's, we can do that if you like. Are you comfortable with x, little x's here, or q's?
That's fine.
Okay. So this is partial, this is a derivative for some product. I will just expand it. So let's expand it here. So it's summation of j equal 1 to n of what? xj. This guy carries over. So I'll do that. Summation k equals 1 to n. xj, this guy carries over y, so partial yk, partial little xj, partial f, partial xk, plus the other way around, which is xj, yk, partial square f, partial xj, partial xk. Okay? Okay. So first of all, the Lie derivative, as you can see from here, components some vector times first derivative of a function. We have, how did we get this guy? How did we get this guy? Actually, this was summation j1 to n xj partial xj acting on f, right? This is the definition of the vector field x. A vector field x has components, large x1 up to large xn. Okay, x1 up to xn. Okay, it's x1 in the e1 direction, xn in the en direction. But as we said in differential geometry, our bases, they are not ijk or e1 up to en. They are partial x's, okay? So whenever you have some components multiplied by partial x's in differential geometry, it means that this guy is a vector field. It means that this guy is tangent to your surface. Unfortunately here we don't have first derivative, we have second derivative. So I cannot write this guy as Lie derivative of my function along some vector v for some v in gamma m. I cannot do that. Why? Because there are second derivatives. Okay, so what about the other way around? LX, LY. What about LY, LX? Well, this is not any different. Just replace x's and y's in this expression. Let's do it. So this is summation j1 to n, summation k1 to n. I'll replace x's with y, so this is y, x here. X's with y, so this is y, x. And again, I have the second derivative, it's the same thing. So this expression is not the lead derivative of your function on the vector. But you can notice now, if we subtract this guy minus that guy, so Lx, Ly, f minus Ly, Lx, actually I take f as a common factor, is simply what? Let's subtract. If you subtract these two, I'll give you some time to write, but just bear with me for a minute, please. These indices, I'll just put them arbitrary, so I can swap them, but if you want to swap them, you have to swap everything. So if you replace k with j here, I have to do it here as well, which is fine, because this can swap easily. If you swap this j and k, you'll get the exact same expression as here. So when you subtract, the second derivative goes away, and what you will end up is the following. Summation k equals 1 to n of summation j equals 1 to n. I also swap the order. Partial yk partial little xj times large xj minus the other way around, partial xk partial little xj times yj. This is all multiplied by what? Partial xk times f. I'll give you some time to write. Even if you miss something, lectures are there, you can go and get it. But here's what is important. Look at this. This is summation over something from 1 to n. Some component, I don't really care what it is. Partial xk, right? Summation k1 to n partial xk. This is indeed a vector field. And this is indeed the lead derivative of f along that vector field. This vector field seems complicated, but what I need to get is that this complicated thing is a vector field. Okay? So this leads us to the next word, which is, and hopefully, it's not the final word for sure, but maybe the final word today, we'll see. The Lie bracket. What's the Lie bracket? Well, I'm given two vector fields on M. Two vector fields, two vectors. And I'm defining the Lie bracket between these two vector fields. It's x and y. It's a bracket, x comma y. This is what we denote. It's defined as this guy. Lx, Ly minus Ly, Lx. In components, it's simply partial y as a vector, partial little x times x minus partial y, partial x as a vector, partial little x times y. So bear with me for a minute here, please. I started with two vectors. What is really important about these two vectors? What's really important is that they are vector fields. Vector field is not any vector, it's a tangent vector. It's tangent to your surface. Okay? I do this mathematical operation. What's this mathematical operation? It's straightforward. If y is an array, is a vector of components, differentiated with respect to the coordinates, this is what's called a Jacobian, right? So you get a matrix here, multiplied by x. Minus the other way around. So the derivative of one times the other, minus the other way around. This is a matrix sum is a vector, you get a vector. The same here, subtract the two vectors together. We're gonna do several examples. The result is a vector. Again, the main point is that it's not any vector. It's a tangent vector, it's a vector field. So the lead bracket between two vector fields, mathematically, or how you're gonna compute it, you compute it this way. The resulting vector is a tangent vector, is a vector field. So what's interesting is that here for this operation, the result's a vector. It's not a vector field. The result here is not a vector field. But magically, when you subtract them, you will always, for any manifold, get a tangent vector. Okay? For any surface, given any surface, in Rn or whatever, given any surface, you can get first tangent vector. Okay, this vector is tangent to that surface. Second tangent vector. Okay? If you do this operation, you will not necessarily get a tangent vector. If you do this operation, you will not necessarily get a tangent vector. But if you subtract them, always for any surface, at any point, gives you a tangent vector. Why we do care about tangency? Because tangent vectors represent possible velocities for your system. Remember, these tangent vectors are the possible velocities. If your vector is not a tangent vector to your configuration manifold, then it doesn't represent an allowable velocity. Okay? Let's have an example. The differential geometry has deep concepts, but the good thing about it, as far as the exam is concerned, is that all the computations are simple. The concepts have deep meaning indeed, but the computation at the end of the day is just differentiation. So, interesting example. I have X vector field, here are the components, Y minus X and 0. And Y, we have colors here, just to help you visualize things. So this is little y minus x and 0, and this guy is maybe 0, z, and negative y. These two vector fields, anybody can understand this? What do I mean here? What's this 2, first of all? What's this 2?
Sphere.
The sphere, you have the sphere. So what do I mean by here? These two things are vector fields on the sphere. They are always tangent to the sphere. At any point gives you some direction, but this direction is tangent to the sphere. So here is your sphere with my very bad drawing. X, Y, and Z. The blue vector actually is the vector of flying westward. Okay? On the sphere, it always gives you something like this. Okay? This is your blue vector. Any question about that? It's always tangent to the sphere. The red vector is this guy. Okay? So maybe at this point, okay? At this green point, these are the two vectors forming the tangent space, the tangent plane, okay? Any questions so far about these vectors? Any confusion about what do you really mean by a vector field? I think this makes it a little bit obvious, right? Oh, yes?
So, if you had a vector that wasn't a vector field that wasn't tangent to the surface, does that even exist then? Like you're talking
This
about?
is a very, very good question. Why? I can have here some vector like maybe perpendicular to this field. That's fine, but this is because you embed your manifold, your surface, in a higher dimension, and this guy indeed lives in the higher dimension. Okay? But in many cases, we don't see, we will not be able to see outside of our world. So I will not be able to even see any vector that is not a tangent vector. So this is why we're really interested in identifying what are the tangent vectors, because these are, from the differential geometry point of view, these are the vectors that we care about. Any vector that is not a tangent vector should not exist from this point of view. From mechanics point of view, we care about tangent vectors because they are possible velocities for our system. Okay? Yes, so if we are talking about this manifold is not a curved space like this nice one, is a space of matrices, special orthogonal matrices. Then I will not be able to talk about anything but tangent vectors. I will not be able to see. Okay? Okay, I have two tangent vectors here, okay? Any question about that? Let's do this guy. Let's do partial y, partial little x's times large x. This is very easy. Get the Jacobian of the y's, please. Let's look how we do it, please. Just bear with me for a minute. This is your y, and you're going to differentiate each component with respect to the three things. So this is 0, that's fine. The z differentiated with respect to x, y, and z. So this is 0, 0, and 1. The negative y with respect to x, y, and z. So this is 0, negative 1, and 0. Any question about that? Times the x component as is, y negative x 0. Okay? Minus the other way around. So consider this blue guy, differentiate each component with respect to all the coordinates. This y with respect to x, y, and z. So 0, 1, and 0. This negative x with respect to x, y, and z. So this is negative 1, 0, and 0, and all zeros. Then multiply it with y, the other vector. 0, z, and negative 1. Any question about that? See, it's pretty straightforward, nothing fancy at all. Any question how to compute it? I mean, you will have to compute it in the final and in your homework full. Any question? Okay, let's get the result. What's the result here is zeros, and this guy is also 0.
X.
And this guy is what?
X.
X, right? Very good, thank you. This guy is minus, we get here,
Z.
oh, I'm sorry. Just, this is the Lie bracket, right? Now let's get this first. Let's get this first. So this is 1 partial y partial x times x. Here's partial y partial x times x. This is, as you said, this is 0, 0, x, right? So here is, I started with two vector fields, always tangent to the sphere, x and y, which means that they are possible velocity vectors. If you have an airplane and flying, this is a possible velocity vector.